In recent times, the machine learning community has been abuzz with the emergence of a groundbreaking neural network architecture known as Kolmogor-Arnold Networks (KAN), positioned as a potential successor to the Multi-Layer Perceptrons MLP. KAN has attracted significant attention due to its claimed superiority in both accuracy and interpretability, all while boasting fewer parameters. Inspired by the Kolmogor-Arnold representation theorem, KAN innovatively replaces fixed activation functions with learnable functions, primarily leveraging univariate splines for parameterization. This unique hybrid structure, which blends the familiar MLP framework with splines, grants KAN's exceptional flexibility and the ability to learn and optimize complex functions with remarkable precision. The paper further explores techniques like simplification and pruning to streamline networks, resulting in reduced complexity, smaller sizes, and enhanced interpretability. Beyond merely outperforming MLPs, KAN holds promise for shedding light on new physics and even the re-examination of fundamental principles, such as the relativistic addition of velocities. Nevertheless, the paper doesn't shy away from addressing trade-offs between KAN and MLP, notably in computational efficiency and parameter count, offering a comprehensive understanding of this emerging architecture. A Kolmogor-Arnold network, or KAN, is a neural network that is trained by learning the activation function at each node, rather than the weight on each edge as in a traditional multi-layer perceptron. This is a practical application of the Kolmogor-Arnold representation theorem. The Kolmogor-Arnold theorem illustrates a key concept on a bounded domain. A multivariable continuous function, f, can be expressed as a finite combination of single-variable continuous functions. This has important implications in the field of machine learning because it implies that the learning of high-dimensional functions can be transformed into the learning of one-dimensional functions in polynomial quantities. However, this theorem suffers from so-called pathological behavior in practical applications, making it difficult to learn possible fractal functions, which limits its application in machine learning to a certain extent. Kolmogor-Arnold network has following features. Learnable activation functions. A distinguishing feature of KAN is its utilization of learnable activation functions, positioned at the edges of the network rather than at traditional MLP nodes. This implies that each weight parameter is replaced by a univariate function, such as spline functions rather than a fixed numerical value. Absence of linear weight. KAN dispenses with linear weight matrices, a departure from traditional MLPs. In KAN, weights are represented as univariate functions, enabling the network to learn complex function mappings more flexibly. Based on Kolmogor-Arnold representation theorem, the design of KAN is inspired by the Kolmogor-Arnold representation theorem, which suggests that multivariate continuous functions can be represented as finite combinations and additive operations of univariate continuous functions. Higher accuracy and interpretability. KAN demonstrates higher accuracy in data fitting and solving partial differential equations compared to MLPs. Additionally, KAN's interpretability is superior as their structure and activation functions can be intuitively visualized. Faster neural scaling rule. Theoretically, KAN possesses a faster neural scaling rule compared to MLPs, implying that as the model size increases, KAN's performance improves more rapidly. Sparsity and pruning. KAN can reduce model complexity and enhance interpretability through regularization pruning techniques. This includes using sparsification techniques to reduce the number of activation functions and pruning away unimportant nodes or connections. Symbolification. KAN offers a method to convert trained networks into symbolic formulas, which is particularly useful in scientific discovery and mathematical problem solving. Local plasticity. Due to the locality of spline basis functions, KAN can avoid catastrophic forgetting issues, i.e., it does not forget old tasks when continuously learning or learning new tasks. Structural flexibility. KAN can adapt to different problems by altering the shape of the network, i.e., the number of layers and widths while maintaining its core characteristics. In a standard MLP, activation functions are typically applied to the neurons, but in KAN architecture, these are placed on the edges and employ these spline functions. For example, a piecewise linear function can be efficiently expressed through a combination of ReLU and linear segments. In a scenario with an input neurons, M output neurons in a piece-wise function divided into case segments. A conventional approach would require NMK parameters. It reduces this by duplicating the input across case segments, applying a shift to each copy, and using weight LU and linear layers to process them, thereby optimizing the parameter count.